Before materials can be used in the battery, they need to be analyzed on quality, ex situ, in situ or operando. The method we describe here concerns Mös-Bauer spectroscopy, which is a method not so well known and not so often used. This is because it analyzes only several elements in terms of oxidation state and environment, providing information on performance and stability during operation. The element that is mainly analyzed is iron as metal or as ion, which obviously is an important element in our battery work. Therefore, Mös-Bauer spectroscopy is an analytical tool using gamma rays, and it is not so often used since it is only active or sensitive for a selected number of elements, here assigned in the blue boxes in the periodic system. Because the method uses gamma rays, these rays also require a source, and also the sources are limited, as shown here in the periodic table with the elements in red boxes. But how does Mös-Bauer spectroscopy work? The Mös-Bauer effect consists of the nearly recoil-free emission and absorption of nuclear gamma rays in solids. This nuclear spectroscopy is sensitive to very small changes in the chemical environment of certain nuclei. When a free nucleus absorbs or emits a gamma ray, it recoils to conserve energy, just like a gun recoils after shooting a bullet. Nuclei bound to a crystal lattice conserve energy when they absorb or emit gamma rays from a nuclear transition, as they are fixed, meaning they stand still, so their movement is restricted. This restriction is the recoilless nuclear resonance, the Mös-Bauer effect. Since for this analysis we need to have a source for gamma rays, several sources are available, but they need, of course, to emit the correct wavelengths of the gamma rays for absorption by the target atom. The elements that are suitable are shown here in the periodic table in blue. The gray shaded ones are neither used as source nor sensitive towards gamma rays with respect to Mös-Bauer effect. To further explain how Mös-Bauer spectroscopy works, we must dig in a little more in the system and equipment as shown in the next slide. So we need the source emitting gamma rays with the same energy as the energy that is absorbed by the sample to assure recoil-free emission and absorption. The emitted gamma rays are generated by an electron bombardment arising from a transducer. With the detector, we then monitor how many gamma rays are being transmitted through the sample. In doing so, we first must bring the emitter and absorber in resonance to monitor the absorption. It is necessary to fine-tune the gamma rays energy. In more detail, the source, where the atoms in the source emitting the gamma rays, must be of the same isotope as the atoms in the sample absorbing them to assure recoil-free emission and absorption. The source often is cobalt for analyzing iron because the energy levels for emitting and absorption are close to each other. The cobalt source unfortunately decays due to emission of the gamma rays, and therefore we regularly must refresh the source by a new one or activate the old one in a nuclear reactor, such as we have in Delft at our reactor institute. If the energy of the emitting and absorption gamma rays are exactly the same, we would expect an absorption spectrum as shown here. But this is usually not the case, because the emitting gamma ray energy is a little off from the absorption energy, and therefore we must fine-tune the absorption gamma ray energy towards the emitting gamma ray energy. This difference is actually very small and can be overcome by moving the radiation source back and forth, which thus shifts the energy and can be regarded as by exploiting a Doppler shift. This Doppler shift is very well known by a passing car or ambulance, where the frequency you hear is higher once the car or ambulance is approaching you and lower once it is moving away from you. This Doppler shift has been indicated here as a blue shift, thus higher energy of the source by approaching the sample, and a red shift due to the lower energy once the source is moving back. Recording then the absorption, we use this moving speed as the running parameter, as you can see in this example spectrum, and is typically in the order of millimeter per second and thus very small, certainly compared to the energy of the gamma radiation itself. Therefore, we may regard this as recoil-free or near recoil-free absorption. In the end, we would like to measure several material properties by the interaction of the gamma rays with matter. In that respect, Mös-Bauer spectroscopy can help us with the following. With Mös-Bauer spectroscopy, 3 types of interactions with the nuclei of the atom are identified. An isomer shift, IS, due to the difference in nearby electron densities, quadrupole splitting, QS, due to the atomic scale electric field gradients, and magnetic Siemens splitting, due to the non-nuclear magnetic fields arising from the surrounding magnetic atoms. These 3 interactions will be explained in more detail, starting with the isomer shift. To recall, the isomer shift occurs due to differences in nearby electron densities at the nucleus of an atom. This is seen as an electron monopole, read Coulombic interaction, meaning the interaction spherically around the nucleus and happens mainly between the protons in the nucleus and the electrons in the closest shell around it, the S shell. This will lead to a chemical shift of the adsorption peak, measured with the Doppler velocity, as we will see in the actual spectrum. The peak in the spectrum thus will be shifted with a value indicated by the purple delta, and thereby reflecting the isomer shift. The value of the shift tells us something on the oxidation state, electronegativity of the surrounding species of the atom, the character of the bonds with the species, and the spin state. Besides the isomer shift, gamma rays interact with the nucleus, where neutrons and protons are unevenly distributed, leading to an atomic scale electric field gradient. This is reflected in the different charges at 4 sides of the nucleus, and therefore this interaction is called quadrupole splitting. This then gives a potential difference around the nucleus at 4 different sides, and therefore it is called quadrupole interaction. This leads to splitting of the peak, also called quadrupole splitting, and is indicated in the spectrum by a green capital delta. The value of the splitting tells us something on the molecular symmetry, the oxidation state, the character of the bonds with the species, and the spin state. If the atom under consideration is further affected by a non-nuclear magnetic field arising from surrounding magnetic atoms, the peaks will be further split up, as seen in the spectrum. This splitting is referred to as magnetic Siemens splitting and is not related to the nucleus of the atom itself, but from the environment where the atom resides. It can be regarded as a magnet working on the atom under consideration. Therefore, it provides us information on the environment of this atom. To understand a little bit more on how this splitting occurs, we must dig into the electronic energy levels of the atom. The number of the peaks and the value of the splitting tells us something on the magnetic interaction, such as ferromagnetism, antiferromagnetism, etc. The consequence of all these interactions will be seen in a spectrum that is recorded. A typical Mös-Bauer spectrum consists of a plot of energy transmissions versus a series of Doppler velocities of the source. The splitting as recorded in the spectrum finds its origin in the splitting of the energy levels caused by the various interaction of the atom and its nucleus and environment. A full analysis of the energy levels goes beyond the focus of this MOOC, but the quadrupole splitting leads to two more energy levels, giving rise to two absorption peaks. Similarly, the external magnetic field further splits up the energy levels, leading to 6 different absorption peaks. Mös-Bauer spectroscopy produces a fingerprint for each material on the basis of the hyperfine parameters, including amorphous phases. In fact, it means that this fingerprint is a specific atom or ion that can identify its ionic, electronic, and magnetic state. Unfortunately, it is only sensitive for a selected number of elements. Luckily for us, many electrode materials will contain iron now and in the future, and it is one of the most abundant elements on Earth. Taking then iron as an example, we can clearly identify isomer shifts and quadrupole splitting of iron-containing phases, and these vary systematically as a function of the iron oxidation state, shown in the green for iron 2+ and brown for iron 3+. It also provides information on the iron coordination, assigned between brackets with an increasing coordination number, shown by increasing darkness of the green and brown color. This all is roughly summarized in this diagram, showing iron 2 and 3+, as well as the various coordination numbers of the iron ion. A specific iron 2 and 3+ spectrum is presented here, showing indeed a large isomer shift and a wide splitting for the iron 2+ compared to iron 3+. This then can be applied to, for instance, lithium iron phosphate, a very common lithium-ion battery material that changes its oxidation state during charging and discharging, and thus can be monitored operando with Mös-Bauer spectroscopy.